Hey everybody, hope your day is going well. This is going to be our first flipped classroom of the year. So let me explain a little bit how this works. What you'll see on the screen is basically me doing the notes live in front of you. And of course you're going to be hearing my lovely voice as we cruise along through these notes. What I strongly encourage you to do is to not just write down what I write down, but to also write down some of the words and explanations that I'm giving, because that really is the critical thing. I'll write down some stuff, but I'll explain more in words, and then you translate that into your own words so that it makes sense to you. Please feel free to rewind and pause me at any time and go back and listen to anything you didn't understand. As tempting as that might be, try not to mute me, because then you'll be missing out on some very important information. So I'm going to try and go through these relatively quickly. It's going to be a long video because we are doing quite a few topics. So I'll go quickly, so if you need to pause me, feel free to do so. Okay, so the first thing we're going to do is I'm going to quickly review how you change from standard form to slope-intercept form, and the next slide we'll go from slope-intercept form to standard form. So standard form is when we have both x and y on the same side of the equal sign. So if we look at this equation here, I see that I got x on the left side and y on the right side, and I don't really care where this is. It could be on the left or the right side. In this case, it's on the right side, but that means that this equation here is in standard form. We want to get that into what's called slope-intercept form. And slope-intercept form is when you have y by itself. That's a very critical thing. So what I'm going to try and do is I'm going to try and get this y by itself. Or another way of saying that is I'm going to isolate y, or I'm going to solve for y. If I'm solving for y, that means I need to get rid of everything that is on y's side of the equal sign. Just like when we solve equations and we isolate x, here I'm going to isolate or solve for y. So the first thing I want to get rid of, if we go back to thinking of cups and beans, I'm going to get rid of this 3x here because I don't need that on the left hand side. So I'm going to get rid of that first, and I'm going to get rid of that as well. So then on the left hand side, I'm left with, and this is a critical thing, negative 5y. This negative right here is connected to the 5. It's attached to the 5. So it's going to be negative 5y. And then on the right hand side is another critical thing, and you have to write this correctly so that it's in slope-intercept form. So the way I want to write this is always with my x term first and my constant last. 20 is called a constant because there is no variable attached to it. This here is the x term, and the negative 3 is called a coefficient. So negative 3 is a coefficient of x, and 20 is a constant in this equation. So I'm going to write it so that I have my negative 3x and then plus 20. Okay, and then the last step that I need to do to get y by itself, I need to get rid of that negative 5. So I'm going to divide both sides by negative 5. So I divide the left side by negative 5. And then I have to divide the entire right side by negative 5. Again, that's a critical step. Make sure you're dividing everything. So then we hopefully are noticing by now that we've got some beautiful ones right there. So I get y equals, and then on the right hand side, I'm going to write this in two separate expressions, or terms I should say. So the first term is going to be when I'm dividing and the signs are the same, that means the answer is going to be positive. So that's going to be 3/5 x. And then when I'm doing these two numbers, I have a positive divided by a negative, so the signs are different, which means that my answer is going to be negative, so that's negative 4. And this is considered slope-intercept form. We're going to talk a lot more about slope-intercept form in later slides, but for right now, that's slope-intercept form. So now we'll take a look at how do we go from slope-intercept to standard form. When we're trying to go from slope-intercept to standard form, I'm basically going to do the reverse process. In this case, I want to get both x and y on the same side of the equal sign. And typically what we do is we'll move the x term, or whichever term is with my constant, I'm going to move that to the opposite side versus taking the y and moving it over here. So I'm going to take this term right here, and I'm going to move it over there, and then we'll do one last thing to make sure that it's completely in standard form. So now, basically what I want to do is I want to move the x term. So the way I do that is I'm going to subtract 3/7 x from both sides. Subtract 3/7 from there. Subtract 3/7 x from there. So then what I get on the left-hand side is, it doesn't really matter how you write this, x or y first. I'm going to go ahead and write the x first. So I get negative 3/7 x plus y is equal to negative 10. Now the last thing that I want to do when I have it in standard form is I don't want to have any fractions in my standard form if I can avoid it. So that means that I need to get rid of this fraction right here. And we learned over the last couple of days how we get rid of fractions. If we want to get rid of a denominator, then we multiply by what we want to get rid of. So I want to get rid of that 7, so I'm going to multiply by 7. And when I do that, I want to make sure that I multiply this by 7, this by 7, and that by 7. Just like when we were doing fraction busters, I need to multiply every term by 7. And again, hopefully what we notice here is those make a beautiful 1. So I'm left with negative 3x plus 7y is equal to negative 70. And then this is considered standard form. Okay, so we've just switched from slope-intercept form to standard form, and then we'll be using these equations later in our graphing. Now we're going to go on to finding the slopes of lines. Okay, so when we're finding the slope of a line, what that is, let's talk about what a slope is. So we probably have some vocabulary for slope. You may remember back in the day when you first learned this, that slope was something over something. We kind of say it as almost rhythmically. Slope is equal to blank over blank. So some of you may be remembering right now that it was rise over run. And I don't have a problem with that. That's pretty good. I think it's a little bit incomplete or confusing for students because we don't always rise. Sometimes when we're doing a slope, we're not going to be rising. We're actually going to be falling. So what I include with my slope is not just rise over run, but it also might be fall over run. And we'll take a look at that. And then the last thing that I want to make sure that you understand is that when we say rise over run or fall over run, we always run to the right. We never go left. If you do and teach your graphing this way, then your students are not going to make very many mistakes when graphing slope. So we rise or fall, and then we always run to the right. We rise or fall, and then we always run to the right. And then the last thing that I want to say is the letter that we use for slope. So slope equals the letter M. And I used to think that it was like some, Latin word for slope or Greek word for slope or whatever. And I used to tell my students that, and then a couple of years ago I decided to actually look it up, and that's not what it is at all. It actually, M is the initial of the person who came up with this idea of what slope is, and is a French mathematician. His name was Montlier. So he used M for the slope because he's the one that kind of discovered it. So that's why it's M. I kind of like the M though, because if you think of what an M looks like, in fact, I'm going to draw this a little bit better if I can. Whoa, didn't mean to do that. The M here, if we draw it a little bit better, it kind of looks like a mountain. And what do mountains have on them? Mountains have slopes. And so an M is actually a nice letter to use because mountains have slopes. The M looks like a mountain, and M is what we use for slope. The other bit of vocabulary that we need to use or make sure we're clear on for this part is this idea of lattice points. Okay, lattice points are points on graph paper. So if I'm going to point to them here, and you can describe them however you like. So lattice points are where this lattice line here, these lattice lines on a graph, and these lattice lines here, lattice points are the points where those two lattice lines cross. So those two lines cross there, they're an intersection of two lattice lines. That's what lattice points are. So you should write yourself a definition here of how you would explain it to yourself on what lattice points are. They are intersections of two lattice lines, or however you like to say that. Okay, so now when we do slope triangles, we're going to do these a lot. I think it's a great way of doing finding the slope. You're going to draw a triangle, and here's a couple of things. You always want to start on the left-hand side of your line. Start at left lattice point. Okay? And so you're going to start your leftmost lattice point. So then the very first thing that we're going to do, if I'm doing this first line here, I'll do this one here first. I'll call that point, or line A. And this one we'll call B down here. Okay, so if I'm going to do A, the very first thing I do is I got to find where my lattice lines are crossing my line I'm talking about at an actual lattice point. So I see it looks like I have a lattice point right there, and a lattice point right there, and a lattice point right there. So I see 3 lattice points where it looks like my line is going through those corners pretty well. It doesn't matter how many there are as long as you have at least 2. So I'm going to start at the leftmost point. So I'm going to start right here. And so what I do for my students to remind them that that's the start is I put a star there, because that is the starting point. So I put a star there, that's where I'm starting. Now the other things that I do, now I'm looking for another lattice point. I always want to go to lattice points. I've got one there, and I've got one there. It doesn't matter which one your students go to. So as long as you start at a lattice point, and then you go to a lattice point to its right, it doesn't matter. So I'm going to go ahead and just go to this one here. And because when I get there, I'll be done. So I have my students put a smiley face because we're done with this one. So now I just got to draw a triangle. And one thing you have to do for some students who have spatial issues is you have to make sure they draw on lattice lines. They can't cross over lines. So slope is either rise or fall over run. Since I'm starting up here and I need to get down here, that means I'm going to fall. So this is going to be a fall over run. So I'm going to start at my lattice point here, my starting point, and I'm going to go straight down like that. And I have my draw a little arrow there like that. And then I'm going to go to the right, because I always go to the right when I'm doing my graphing. Now the only other thing that they need to figure out is how did they move? Well, since I fell, and when things are falling they're going down, we call that a negative. So I went down, or negative, and then I count boxes. The best way to count is to count outside your triangle. 1, 2, 3, 4. So I went down 4, and then I went to the right 1, 2, so that's 2. So then my slope is equal to m is equal to -4 over 2, which is equal to -2. And you can leave it as a fraction, or simplified fraction if you want, whichever. Okay, so there we go. So that's one example. Now, here's another example. I'm going to start at the leftmost point. So the first thing I'm looking for is lattice points. I see a lattice point there, and I see a lattice point there. So it looks like I have 2 lattice points to choose from. I am not going to start here because I always start at the leftmost lattice point. So I'm going to start over here. So that's where I'm going to put my star. And I'm going to go to this lattice point here. That's where I put my smiley face. Now, for this one, I'm starting at this lattice point and I'm going up to this lattice point, which means I need to rise. That's a requirement for me to rise and then run to the right. So from the star, I'm going to go up 2. I went up 2, and since I went up, I'm going to make it positive. I don't need a negative because I'm not going down. So I went up 2, and then I go to the right and I went to the right 1, 2, 3, 4, 5, so I went to the right 5. So for this one, my slope, m, is equal to a rise of 2 and a run of 5. And there's no simplifying there. It's just 2 over 5. Okay, so that's how you do slope triangles. Last couple of quick things here, I'll talk about it. You can quickly see if your students or if you are doing these correctly, because your triangle should always be on the left-hand side of your line. So if I shade in these triangles a little bit, and we see that my line is going like this is on the left-hand side of my line. My triangle is not down here below it on the right-hand side. This is a little bit easier one to see the left and the right hand. So here's my triangle. This triangle is on the left, or here's my line, excuse me. This triangle is on the left-hand side. It's not drawn over here. Technically, you can get the same slope, but your students will make more mistakes if you allow them to draw it on either side. If you say they must always start at the leftmost point and then rise or fall and always run to the right, then their triangle will always be on the left-hand side of their line. Okay, take a look at the next one. Okay, now we're going to find the slope of a line given 2 points, and we're going to use something called delta y over delta x. So delta y over delta x, delta is a Greek symbol. For those of you that are in fraternities and sororities, you already know this. Some of those you that aren't may not know it. And that symbol looks like this. It's a triangle. So we have delta y over delta x. And the symbol delta stands for change of. Okay, so what we're looking for is the change of y over the change of x. So what I need to remind myself of, or our students of, is that this is my x and this is my y. So I'm going to go ahead and plot point A. So if I plot point A, so I put a dot here, and that is the point 10. I'm actually going to move it over a little bit. Actually, yeah. I'm going to move it over just a tad here. So here's my point A. And so that's the point 10, 7. So if I think about where point B would be, well, point B, my x value is 4, and if this is at 10, then that means 4 is going to be over here somewhere. So that means that my point B is going to be to the left of point A. And since it's only 2 and this one is 7, that means it's going to be the left of point A and it's going to be down. So it's going to be somewhere down here is going to be point B. And that is the point 4, 2. So now I still want to draw a triangle. So I want to get to this, I want to get from this point, that's my star, to my happy smiley face, and I'm going to draw another triangle because that's my 2 slopes there, right there, or my 2 points, I mean. So I'm going to go up here and that direction like that. So I went up and then to the right. Now, how many did I have to go up? Well, if I started at 4 here, and then I went up to 10, then that means this height must be 6. And if I started at 2 here and went over to 7, then that must be 5. Whoops. So then my slope is going to be m is equal to, in this case I had a rise, so I rose 6 and I ran 5. And we don't need to worry about an improper fraction. That's perfectly okay. We don't have a problem with that at all. Okay, looking at the next one. So I'm going to do the same thing here. So there's my x, and here's my y. I'm going to plot my point A, or excuse me, my point C is right here. And so it's going to be, that's point C, which is -3, -6. And then I'm going to plot point D. So if I look at point D, D is, so if this is -3 and this is 2, that means that it's going to be to the right of it. And then if this is -6 here and that's -8, that means it's going to be below. So it's going to be, shoot, I can see I need to move that, don't I? Put that in the wrong spot. It's going to be somewhere over here. It's going to be the right and then down. And if you give me just a brief second here, I am going to make this a little easier for us to look at here. Okay. And so this point C, whoa, didn't mean to do that. Point C is going to be -3, -6. Okay, so now I'm going to draw my slope triangle. So I'm going to need to go to get from, here's my smiley face, and then to the right, always to the right. So this case, I went down. So I went down, and so I started at -6, and I went down to -2, or excuse me, -8, that means I went down 2. And then here, I went from -2, which is here, and then to +2, so that means I went -3 to get to 0, and then I went 2 more to get over there, so I went a total of +5. So then my slope is going to be equal to, m is equal to a fall over run this time, which is equal to -2 over 5 for my slope. Okay, so that's my slope for finding using delta y over delta x, or change of y over change of x. Okay, on this one, we're going to use finding the slope using a formula. And some of you may remember the formula from way back in the day. The formula was slope, which is m equals y2 minus y1 over x2 minus x1. So in this case, what we're going to do is we're going to use these 2 points, this point here and this point here, and we're going to plug them into this formula. So what we need to do is we need to figure out, or decide really, which point we want to be A and which point we want to be B. I don't care which it is, and neither should you. So we're just going to make arbitrarily, we're going to make this point A, or excuse me, point 1. And then this one is going to be point 2. Okay? So then I'm going to say, okay, I'm going to plug in my my values for y and x. Now, one thing I want to point out here that I didn't mention too much in the last slide is, please note, very importantly, that y is always the numerator and x is always the denominator. If you look back at the last slide, it was delta y over delta x. Slope is the change of the height over the change of the width. So it's how high we're going over how far left or right we are going. That's a critical thing. If you flip these two around and put delta x over delta y, you get it wrong every single time. So we've got to find the change of y over the change of x. Okay? These don't really matter. The 2 and the 2 and the 1 and the 1 don't really matter which point is 2 and which point is 1, as long as you keep it consistent. So this is going to be a point, and this will be the other point. It doesn't matter if you make this point A and this point B, or if this point B and this one point A. So, okay, I've made my decision, so I'm going to stick to it, but I just wanted to make sure I point that out. It's always y over x. Okay, so then my y2 is right here. So that's 1. So slope is equal to 1 minus my x, or my y1 is right there. So that is minus 5 over my x2 is right there. So that's -5 minus, and then my x1 is right there. So that is 2. So what I want to emphasize here is, notice that the point 2, which is in blue, is stacked above each other. 1 and -5, 1 and -5. The point 1, which is red, is stacked above each other. So that is 5 and 2. So that's critical. This has to be this point, and this has to be this point. Okay, now at this point we just do some simple subtraction. So 1 minus 5 gives me negative 4. And then over here, I'm not sure if you guys remember how to do this, but I go boom, boom. So negative 5 plus negative 2 gives me negative 7. And then when you're doing division, if you're dividing this, the numbers that have the same sign, then your answer is positive, which means this is really going to be 4 over 7. So the slope is equal to 4/7. And that's the slope when you're given 2 points. So it's y2 over y1, or excuse me, y2 minus y1 over x2 minus x1. Okay, so now we've done a bunch of stuff here, and now we're going to do some graphing of these. So notice that we're using slope-intercept form. The reason we did those 2 slides at the beginning was to be able to change equations into y equals mx plus b form or slope-intercept form. This is probably the most critical equation you need to memorize if you haven't already done so. Is y equals mx plus b. I say this a billion times in my life. Y equals mx plus b. And I say it with that kind of cadence. Y equals mx plus b. Y equals mx plus b. Try and get the kids to hear a cadence or a rhythm to it so it's easier for them to memorize. It's never y equals b plus mx. If your students write their equations like that, please don't allow them to do that. Make them write as y equals mx plus b. So here, I'm going to say y equals mx plus b. So the reason that's important to write it that way is because we see that this is the y and this is the x, which means m must be equal to the 1/3 and b must be equal to the negative 2. So notice that I included the negative with it, right? So the sign goes with the number. So we already know what m is. M is the slope. M equals 1/3. And we should know by looking at it what this is. Since this is a positive slope, this means that it's going to be a rise over run of a slope. What we don't know is what the b means. So b is the y-intercept. It's the point where your line crosses the y-axis. So if here is my y-axis right here, this is the y-axis. So there is a point on this line that is going to cross this y-axis right here. The point where this line crosses the y-axis is right there at negative 2. So the y-intercept is negative 2 for this one. Now, I'm not sure why they use b for y-intercept, but I do like that letter because that b, what I tell my students is it stands for beginning, because that is the point that we begin with. We are going to plot point B before we do our slope. So I begin with my y-intercept. So I'm going to start with that one right there. So the point negative 2, the y-intercept is negative 2, is on the y-axis at negative 2. There's my y-intercept. Now, to do my slope, I know that this is a rise over run. So I'm going to rise this many and run to the right that many. I always run to the right. So from my starting point, not from the origin, but from my starting point, I go up 2, 1, 2, and then I run 3, 2, or I don't go 2, I go up 1, excuse me. I go up 1, and I run 1, 2, 3 to the right. And there's my second point. And then I go up 1, and 1, 2, 3 to the right. So then my line is going to go through those points. And there is the graph for that line. Okay? So that's how I graph a line. I start with my y-intercept, and then I graph my slope. So I'm going to do another one on the same graph. It shouldn't be too bad because we know a little bit more about what the equation means. So I write this again, y equals mx plus b. My m is equal to negative 3, and I want to write that as a fraction, so it's going to be negative 3 over 1. And then my b, or my beginning, is equal to negative 2. Excuse me, no it's not, negative 4. Positive 4. I don't know if I got negative 4. I think I looked up above. Positive 4. Okay? So I'm going to start with my beginning again. Start with my b. So I start here, and my b is going to be always on the y-intercept, or y-axis. It is my y-intercept. So there's my b. From my b, I'm going to do my slope. Since this is a negative slope, that means it is a fall over run to the right. So from my b, so from right here, I'm going to go down 3. 1, 2, 3, and then 1 to the right. Then I'm going to go up and put a point there. Down 3, 1, 2, 3, and then 1 to the right. So I'm going to go ahead and plot those points. I'm going to go down 3, 1, 2, 3, 1 to the right. There's my point. Down 3, 1, 2, 3, 1 to the right. There's my point. And then I can draw my line going through those points, just like that. Use a ruler as best you can to make it as straight as possible, and there's your graph. So we can graph using the slope and the y-intercept. Start with the y-intercept, which is your b, and then you graph your slope. Okay, when it's in standard form, we don't really like this that much, but so what we want to do then is we want to change it into y m equals mx plus b form, and that's what we did at the very beginning of this flip lesson. So I'm going to subtract 2x from both sides, and I get negative 3y is equal to, and here's where I have to write in mx plus b form, so negative 2x plus 9, and then I'm going to divide by negative 3, divide everything by negative 3, so I get y is equal to, when the signs are the same, the answer is positive, so that's going to be a positive 2/3 x. And then here, when the signs are different, the answer is going to be negative, so that's going to be minus 3. And now I have it in y equals mx plus b. So my m is equal to 2/3, and my b is equal to negative 3 over 1. And I'm going to go back here and say this is a rise over a run to the right. Okay, so now I'm ready to graph. So I'm going to graph my y-intercept, which is at negative 3, which is right there. And then from that point, I'm going to rise 2, which is 1, 2, and then run 3 to the right, which is 1, 2, 3. So I'm going to put a point right there. And then I'm going to rise 2, 1, 2, and 3 to the right, 1, 2, 3, and put a point there. And so that would be how the line goes for this equation right here. So this point line right here, that point line right there would go through those, this equation right here would go through these points. This line right here, this line right here is equivalent to this equation right here. Okay, let's take a look at the next one. Okay, so now we're going to go back to the Milt's soda machine demonstration we were talking about a couple days ago. So if you remember, we talked about things that are functioning. And something is functioning if it is predictable. We talked about predictability. If I press a button and I know it's going to come out, then it's a function, or it's functioning. If I press the button and I'm not sure what's going to go out, then it's not functioning. And we assume all soda machines to be functioning before we know they're not. So what I mean by that is, if you've never gotten anything out of a soda machine before, and you go up to it and you put money in it, you only would do that if you think it's working. If it's not working, then you're not going to put your money in there, because it's going to steal your money. So we assume things to be working like they're supposed to be. So we say that they are functioning. So if you go up there, you press a button, and you get out a soda, If you press that button again and it gives you the same soda, then you say it's functioning because it's predictable. Even if it's not what's labeled, it's still predictable. So what makes it difficult is we get our own ideas of what's right and wrong or what should I have gotten, but can you predict what it is? Now, when you walk up to the soda machine and you press the button, you are giving that machine some input. You are giving it some information. The information you're giving that machine is that you want this soda, whatever button you put. So we call that our input. In a graph, we have I have a couple T-charts drawn right here, drawn right here, and the X is our input. Okay, the X is our input. And if the X is our input, then that means the Y must be our output. So when we look at a graph here, or a T-chart, what we're trying to figure out is this predictable? Can I tell if it's predictable? So what I'm looking for are repeated inputs. That's the only thing I care about. If I don't have any repeated inputs, then I have to assume that the graph is going to be a function. It's going to be a function because there's no proof that it's not a function. So when I look at this data right here, all of these points on this for this graph, if I were to take this and plot these on a graph, on X and Y axis, and plot my points everywhere they go, if I were to plot these, of all the points that are here, the only ones I care about are the ones that have repeated inputs. So I see that I do have repeated inputs. The repeated endpoints are my 2 here and here. So these 2 right here, I don't care about. So I'm going to go ahead and circle those. These don't matter because they're unique inputs, which means their information does not help me at all. I'm going to scratch them out. Okay? The only ones that I care about are the ones that have repeated inputs. So now, if this is functioning appropriately, when I do an input of 2, I should know what I'm going to get out. So here I have an input of 2 and I get a 7. I have an input of 2 and I get out a 7. Since that was predictable, or it's exactly what I expected to happen the last time I pressed a 2, I got a 7. Therefore, this graph right here is a function. Okay, so this graph is a function. So now I'm going to do the same thing over here. I've got input and I've got output. The only thing I care about are repeated inputs, and you'll notice the data is pretty similar. I did that on purpose. I wanted the data to be similar. The only thing input I care about are repeated ones, so the ones that I don't care about are right here. I can scratch those out because they're not helping me decide if it's a function or not. The ones that do help me are the ones where I have repeated inputs. So I have repeated input like that. So since I have repeated inputs and I see that when I plug a 2 in, I get 7. The next time I plug a 2 in, I got -6. That is not what I expected to happen. What I expected to happen was for it to be a 7. Since it was not a 7, that means that this is not a function. Okay? So that's how we do it by looking at data, is we're looking for repeated inputs like here and here, and if the outcome is the same, then it's a function, like this one was. If the outputs are different, then it's not a function. So this one over here was not a function. All right, let's take a look at the next graph, chart. Okay, so now we're going to talk about functions that are on graphs. And when we have a graph of a function, then we're going to use a little bit different technique. We can still talk about inputs and outputs, but there's an easier if we do this technique called the vertical line test. So for the vertical line test, we're going to do this. So there's my vertical line. And in the vertical line, whoa, that is not what I meant to do. Excuse me, let me do it again here. In the vertical line test, hopefully it works this time. Yeah, okay. I'm going to take my vertical line, which is not exactly vertical. Let me try and get it vertical now that I've got some graph paper. There we go. And take my vertical line, and I'm going to pass my vertical line across my data from left to right or from right to left. It doesn't matter. So I'm going to take this line right here, and I'm going to start moving it across the graph. Okay, that's what I'm going to do. If at any point when I move this across the graph, if this line ever touches 2 points at the same time, then that graph is not a function. So when I moved my line across, did you ever see it going through 2 points at the same exact time? Doesn't look like it. Each time I move it across, it's just hitting the 1 point at a time. Therefore, this graph we would call is a function. Whoa, that's not what I meant. This is a function. Okay? So, if we look at the next one, and if I can grab it, good. Okay, I'm going to change this back to blue. I think I like it better in blue. Let's see if I can change that to blue real quick. Okay, so this one, I'm going to take this again, and I'm going to move it across, and you tell me, do I ever cross the graph twice? Moving it across every time. Where I'm looking, I know you guys can't see what I'm doing, I'm looking right here. That's where I'm looking. That's the only place I care about, is right where it's crossing this line. Where my blue line is crossing is the only thing I care about. I'm looking right there. So as I move this across, continue to move it across, do we ever see it cross the line twice? And the answer to that is no, it never crosses twice, which means that this graph must be moving around on me. Oh crap, grab it. Ugh. Alright, I'm just going to change it anyways. So that means this graph is a function. Okay, so that's a function. So now, we're going to take a look at this next one here. As I look at the next one, get myself another vertical line here. Start moving this vertical line across. Again, where I'm looking is right here where it crosses the line that I have drawn. That's the only point that I'm looking at. So as I move this across my line, tell me when you see it hit twice, or do you see it hit twice? And right here, I see it hitting here and here. So it's hitting twice. If I continue to move it across more, then I see, oh my goodness, I'm hitting 3 times. I got 1, 2, 3 times. It doesn't matter if it hits once, or if it hits twice or 3 times or 100 times, it's not a function. So because this line right here is hitting this line right here, there, and there, that means that this graph is not a function, and it doesn't matter that it's a function over here, and it doesn't matter that it's a function over here. 1 point can make it not a function. That's all it takes, is 1 point. It only requires 1 time for you to expect what you're supposed to get out of my soda machine and it not work, that it's not functioning. So it only takes 1 point. Okay, so next we're going to go to the letter D over here. Whoops. Why is the whole thing going? Alright, I'll just get another one here. Oh, I'm using red this time. That's cool. Okay, as I move across, moving across, did you ever see it hit twice? This is the pencil test or the vertical line test. It does not look like it's ever touching twice, therefore it is a function. It's not hitting, but it is a function. If I keep moving this across over to E, I see right there I'm hitting there and there. Therefore, this one is not a function. So this was yes, a function. And this was no function. Okay, so that's the vertical line test or the pencil test. Okay, so the last slide here, we're going to do two things. We're going to talk about function or not. So we're going to use the vertical line test for functionality. So I'm going to go ahead and give myself a vertical line here. And I'm going to take the, oh darn it, didn't want to do that, didn't want to do that. Let me do my vertical line again here. Okay, so here's my vertical line. Make it longer. I'm going to go up here to A, start moving it across. Okay, start moving it across. Cross, 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 and we get to right here. Now here causes some issues. We have a line with an open circle at the top, right here, and we have a line with a closed circle at the bottom. Students don't always know what this means. So what this means right here means that at this point right here, it's not included at this line, on this line. This point right here is included on this line. So this is like a starting point for this line, but it doesn't include that point. This is a starting point for this line, and it does include that point. So the question we have is this a repeated input? Is this a function or not? And since this circle here is open, not filled in, that means it doesn't exist on this line, which means these 2 points are not stacked on top of each other. So this is, when I do my vertical line test, when I do the blue line going across, my blue line is only touching right here because that one is open. Therefore, this is a function. It is not negated because that is right on top of, because this is right on top of this, but because that's open. Now, if this were filled in, if this were colored in like that, and now I do the vertical line test, then it's not a function because now that point is, this point is covering up that one, and so it's not a function. Okay, but that's not what we had. We had a open one, therefore it was a function. So take that blue out of there, or the yellow and the green. Okay, so that's what we had. So therefore this one is a function. Okay, now moving across again. So I come moving across here. See, nothing hitting there, nothing hitting there. Oh, right there, I'm hitting 2. As soon as I do that, no function. Not a function. Okay. So not a function. Coming across here, you might, this was kind of freaks people out a little bit. If you do the pencil test, it's no problem. What freaks people out is they think, well, what if I did it like this? And then now they're all crossing. And that's true. They are all crossing. But it's not called the horizontal test. It's called the vertical line test. So in order to do the vertical line test, you have to have your line going vertically, like this. So it's the vertical line test. So this one is a function. Whoops. What the heck is I doing here? Function right there. Okay. And then the last one I want to do is this circle one here. Again, this kind of freaks people out a little bit. It shouldn't really. You're cruising across. You're all good right there. The second you come in here, you are now crossing at that point and that point. If you're crossing at 2 points, then that means it is not a function. Not a function. Okay? So that's functions. Now, we have this other thing called discrete and continuous. Okay, so discrete and continuous. Continuous is the easier word to understand. We know things that are continuous. It means they never stop. They don't quit, right? That's kind of the rule, the definition we're going to use. But we want to think of continuous as in no gaps for our x values. So once our line starts, there are no gaps in the x. So if you think about that definition, and we apply it to this, no gaps in our x values. I'm going to get rid of all this junk that I had a second ago. Okay, so we're getting close. Okay, so if I have no gaps in my x values, I have continuous points on my x axis, if I had one. The x-axis is this one here. I don't want to use that color. I use this one. Here's my x. Okay, this is my x. So if I look at this, then I see that even though I have a gap there, it's filled in with this one here, which means that this graph right here, albeit weird, is continuous because there's no gaps in the x. Okay, that's continuous. If I come look at this one, and I see, well, okay, here's my x value, but my x axis, but I see that I do not have a line there, and I don't have any points there, and I don't have any points there or there. So there's no points. That means this has lots of gaps in my x's, so it's not a solid line going across. Then this would be discrete. I don't do it in that color. This is discrete. So discrete is when there's gaps in your values. So if I come look at letter C, obviously this is discrete because I have gaps in between each of these points going along my x. Now I look at this one, and this one causes little students a little bit of trouble because they say, well, there's nothing over here on this side and there's nothing over here on this side. I agree, there isn't anything over there. But what we care about is when my line starts, when my graph starts. So I only care about where the line is drawn. So if I start here and I go over to here, are there any gaps in my x values? Are there any points in my x where you don't have the line drawn somewhere? And the answer to that is no, there's a line drawn everywhere. So since there's a line drawn everywhere, this one is continuous. Okay? So that's discrete and continuous, as you're looking for gaps in the x values. All right, so I'm going to do one more quick one here. I'm just going to draw it in the box of letter C. You can draw it wherever you need to. That graph is continuous because it never stops. No stops in my x values. Okay, so that's discrete, continuous. In fact, that's all the graphing stuff. So we've covered all the graphing in this one video. Take notes on it. I will post some problems to do for you guys to do. We'll have lots of different concepts on it. And then I'll see you guys on Tuesday. And I'll also be posting some problems you should be ready to do for your test on Thursday. Have a great rest of your week, and I'll see you next week.